Hello everybody, my name is Romy and I will present you our work on relational verification of cryptographic implementations in WebAssembly. WebAssembly is a low-level language designed for the web that runs through the JIT engine of a web browser or standalone using a runtime environment. The main compilation pipeline is compiling high-level code in C, C++, or Rust to WebAssembly binary using the LLVM toolchain. WebAssembly is designed with portability, scalability, and security in mind. It features structured control flow and has memory isolation properties. As a result, WebAssembly is used in security-critical applications, including cryptographic algorithms that are vulnerable to timing attacks. Timing attacks are side-channel attacks where the attacker observes differences in the execution time of a program to infer secrets such as cryptographic keys. Timing attacks have been used to infer cryptographic keys in RSA and AES implementations, among others. The following example shows a real-world timing vulnerability taken from a TLS implementation of OpenSSL. The function removes the padding from a decrypted TLS CBC block. So by leaking the padding length, the attacker is able to use the position of the padding to decrypt a ciphertext. The padding length, which we'll refer to as secret here, is stored at the last element of array data. Following the data flow of the secret value in the function, we can see that the number of loop iterations, which affects the execution time of the function, depends on the secret value. So generally, branching on secret values, including loops, is insecure. Continuing the data flow, we can see that value j is used to access an element of array data, and the time for retrieving this data depends on the index value and the cache state in modern architectures. In this way, an attacker that controls the cache state can reveal the secret. So indexing memory with secret values is insecure. Here we have another leak of the same secret value at the if condition. In summary, to guarantee the absence of timing leaks, we need to guarantee that there are no branches on secrets and that no secrets are used as memory indexes. Constant time is a programming discipline to eliminate timing vulnerabilities. Given a security policy which defines which inputs are secret and which are public, constant time prevents execution time dependencies on secret values. That means converting if statements and memory operations to constant time equivalent using logical operations or hardware instructions. There are multiple constant time implementations, including BareSSL, LibSodium, HackleStar, and Treat-Knuckle. Some implementations are implemented directly in WebAssembly, whereas others can be compiled to WebAssembly from a high-level language. So the goal of our work is to verify that WebAssembly programs respect the constant time policy for cryptographic implementations. So the question is how to verify constant time for WebAssembly. To our knowledge, there's one approach to verify constant time implementations in WebAssembly, CT-WASM, which is type-based. That approach is efficient but has two main drawbacks. First, it considers the whole memory as secret and thus requires to rewrite some implementations for verifying them. And second, it requires type annotating the program, which cannot be fully automated. Relational symbolic execution is an approach based on symbolic execution that can be used to verify constant time implementations. In particular, we assume the symbolic execution of two identical versions of a program with equal initial public values but different secret values. That means that if the control flow differs between these two versions, then this will depend on secret values, which would reveal secret information via timing side channels. Also, the index of memory operations should not depend on secret values. Compared to time-based approaches, relational symbolic execution has improved accuracy but has scalability issues. So our approach, Vivienne, takes as inputs the WebAssembly modules and the security policy, which describes which inputs are secret and which are public. The outputs of the analysis is either the successful verification of the algorithm or the identified timing vulnerabilities. To verify WebAssembly programs, Vivienne performs relational symbolic execution. Here we see a WebAssembly code snippet. The security policy defines which inputs are public and which are secret values. Here on the table, local variable 1 contains a secret value and local variable 6 contains a public value. WebAssembly is an instruction format for a stack-based virtual machine that uses a value stack. To understand how our approach works, we will go through this example. First, local variable 6 is pushed to the value stack. Here, because the value is public, the relational symbolic value contains only one symbolic value. Next instruction pushes the content of local variable 1 to the value stack. LV1 is secret and we have therefore two symbolic values describing the two executions. Next, the add instruction takes two elements from the value stack and pushes the result back to the value stack. The load instruction loads from the memory the data with index the top of the value stack. At this point, we need to check that the index does not depend on secret values. To do that, we generate formula phi that checks whether the values of the two versions are not equal. If phi is satisfiable, that means that we have a vulnerability, otherwise there is no vulnerability. Here, LV1 and LV1 prime are different symbolic values, so there are multiple assignments that make the formula satisfiable. That means that we have a bug here. Then we continue the execution until the conditional branch at line 7. Here we need to check again that the condition does not depend on secret values. Loops are one of the bottlenecks of symbolic execution-based analysis. For the default analysis, Vivienne uses unbound unrolling. However, that may lead to large overhead for loops with large bounds. Bounded analysis is unsound. However, automatically generating loop invariants is a hard problem. Instead, we propose a lightweight method to infer relational inductive invariants. The procedure to do that is as follows. First, we find all variables modified in the loop. Then we run symbolically two passes of the loop. We generate a candidate invariant that declares the variables containing public values during the two passes as public. And finally, we perform a standard invariant checking by first generating fresh symbolic values for all modified variables, then assume the invariant holds for the havoc variables, then run the relational symbolic execution, and finally assert that the invariants hold. Here we will see an example of the analysis using our relational invariant approach in a small code snippet in WebAssembly. First, we find all variables that are modified in the loop body, here LV1 and LV4. Then we run symbolically 2 times the loop body and find that LV1 is public and increases its value by 1, whereas in both loop iterations LV4 has a value of 1. With that information, we generate an invariant that indicates that variable LV1 is public and that LV4 is public and equal to 1. Then we assign fresh symbolic values to all modified variables. We assume that the invariant holds. Then we run our analysis to identify timing vulnerabilities, and finally check that the candidate invariant we inferred is valid. Given the symbolic execution has scalability issues, we want first to evaluate whether our approach is practical for constant time implementations in WebAssembly. On the table to the left, we see in the first column the benchmark abbreviations. These are explained in the table to the right. The second column shows the number of algorithms belonging to each benchmark set. The third column shows the number of constant time implementations that were verified correctly. The fourth column shows the number of unsafe algorithms where the vulnerabilities were discovered. The table shows that there are only 2 implementations in gray where the analysis does not terminate. The reason for that is that these implementations contain loops with large loop bounds. In all other cases, Vivienne is able to verify the constant time implementations and find the timing vulnerabilities in the non-constant time implementations. The second question is how effective is relational inductive invariant generation we use for relational symbolic execution. In this table, we can see that the 2 implementations that are in gray that were not analyzed with unrolling are analyzed correctly with the invariant. Also, the invariant generation technique is able to check 57% of the implementations. The rest of the implementations cannot be analyzed due to over-approximations, for example, caused by the lack of constraints on the loop bounds. In our results, there are no false positives, although they may occur. Summarizing, the relational inductive invariant is able to analyze two algorithms with large loop bounds where unrolling does not manage to analyze within the time limit of 90 minutes. However, it does not manage to analyze all programs. To conclude, in this paper, we design a relational symbolic execution approach to check constant time implementations in WebAssembly. We propose a relational invariant generation technique that analyzes more than half of the benchmarks, including 2 implementations not terminating with unrolling. We analyze WebAssembly Haggle Star and the compiled WebAssembly code of libsodium and BearSSL for the first time. If you are interested in our code, you can find it in this repository, and if you have any questions, please contact us. Thank you for listening to this presentation.